Good morning, students, and welcome to chemistry. I'm, of course, recording this lesson from very beautiful and sunny Maryland. It is actually just about as hot and humid as it is in Florida, so I get no reprieve from the intense heat that you guys are suffering through yourselves. Now, you did take a test on Wednesday, and I'm going to give you a chance to take a look at your tests. So, if your substitute teacher would kindly pause this video and pass back the test to those who have taken it so they can see it, that would be wonderful. However, you are not going to be able to get the answers until I get back, because there are some students who haven't taken the test, and there are also students that need some explanation through some of the questions, which I will do when I return on Wednesday. You can pause the video now. Otherwise, let's return to really Chemistry Chapter 2. And it's possible in my haste that I didn't print out your notes, and I apologize for that. But if they are printed out, they will be on the desk. So if your teacher could pass that out, that would be wonderful as we begin Chapter 2. But if not, you're just going to have to take notes the old-fashioned way, and that is to read the notes in your textbook. And of course, that's so less than ideal, but it's just going to be what it will be, okay? Now, let's take a look at Chapter 2, Chemistry, Precision, and Design, on the nature of matter. And this lesson will be a little philosophical, but it's good for us. You see, matter is anything that occupies space and that has mass. Matter, by virtue of being matter, has to have some room to be matter. And if it takes up space, it has mass as well. Now you might be able to think, well, hold on. Air takes up a lot of space, but does air have mass? The answer is yes. A lot of mass, considerable amount. Any one given moment, you have the pressure of air on you about the force of 2 elephants. You don't feel it. Your body, of course, is used to it. It's why when you jump up, you fall down, because there's an immense amount of force pushing you downwards. There's lots of different states of matter: solid, liquid, gas, plasma. We're going to go through those individually. And the state of matter is affected by certain factors. This factor will be an essay question. I believe an essay on your quiz tomorrow, as well as an essay on your test, what affects the state of matter. The nature of the particle present. So it is in the nature of some particles, for instance, mercury, to be a liquid. Nature of some particles like oxygen to be a gas. Nature of some particles like iron to be a metal, a solid metal, that is. And chemical bonds present. So sometimes when certain things bond, it causes a state change. For instance, bonding that you might be familiar with is bonding of iron with oxygen to form iron oxide. Iron oxide is well known as rust. It transforms the oxygen from that gas to a solid with different properties, because it is linked to iron, creating that rust. Temperature, of course, if you heat things up, they tend to be more liquid and gaseous. We can find that very easily. You take some ice and heat it up, and you can make it a liquid and make it into a gas pretty easily. Kinetic energy. Sometimes when things go fast, they become liquids, or maybe when they get moved, they become gaseous. If you put water in a blender and start the blender, the kinetic energy will cause the water to warm. Not a ton, It's not like you can boil water in a blender. That take a lot of motion, a lot of force. But motion does cause heat change and pressure. You ever heard of an Instant Pot? You put your food in, and it uses pressure to artificially cook food. Pretty amazing. And I describe these things in detail: solid, liquid, gas, plasma. Solids have definitive volumes and shapes. They're difficult to compress, and they're packed pretty close together. Liquids have a definitive volume, but no definitive shape. The liquid just takes the shape of its container. A solid will become a liquid at its melting point. Gas has no definitive shape, no definitive volume, and can pretty much take the shape of the room. So in my hotel room and in your science room, if the walls started to compress, one of my biggest fears for some reason, I've never had it happen to me, the gas would also compress. And you wouldn't really know. It might actually be easier to breathe because you're taking in more oxygen because it's less spread out. But it's easy to compress. It doesn't have a shape or volume. But it does have a definitive number of particles that are in it. A liquid becomes a gas at its boiling point. And you might be asking, well, I see plasma up there, but I don't know what plasma is. And that's because I don't really know either. Lots of scientists don't know what plasma is or what it does. It's strange. Once gas gets beyond a certain point, it kind of becomes a liquid again, except this liquid has just odd properties, like the sun. The sun is made of plasma, and the sun is seeable, unlike many gases. But the sun exhibits properties of extreme heat. And when heat is so extreme, it causes these properties to act kind of like a solid, kind of like a liquid, and kind of like a gas. And it's kind of a mixture of all three, but is only for extreme heat situations, which is caused on the sun by the heat of fusion. Hydrogen fuses together to form helium, which is an immense amount of power, more power than any nuclear bomb that we can create. Now, if you will take a look at your periodic table in your textbook, your periodic table is actually, for me, on page 362, very back of your textbook. Periodic table is very enlightening. It says a lot, and says a lot of very cool stuff. We're going to learn a little bit how to read the periodic table. But first, a substance is a form of matter with unique properties to make it different than any other substance. Atoms are the smallest particles that make up a substance. Atoms come in these forms called elements. These elements differ from one another. There are 118 elements out there that we know of. And we are creating more. And we're doing so in a lab. But you can see there are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc. They're all elements. They all have different properties. They're arranged for you on this periodic table. And this periodic table does a wonderful job, a masterful job, at organizing these elements. And as you can see here, there's an atomic number, which lists the order it's in. It also lists the number of protons. We're going to talk about protons in a little while. And you have a symbol, an easily recognizable name. Symbols are useful, right? Because in different languages you call these elements different things. So, for English, you might call carbon, carbon. But, I don't know. In German, it could be something completely different. I actually don't know what it would be in German or Spanish or any other language. Maybe you can look that up yourself. But the symbols stay the same. So we all understand what C means. It means carbon. Pretty easily recognizable. And you have atomic mass, which we'll talk about later. It's not very important now. It's a number below the symbol in the name. Molecules are an arrangement of atoms linked together by chemical bonds. If you have a water bottle on your desk with water on it, you're drinking in a molecule. That is two hydrogens and an oxygen fused together by a chemical bond to form water. Really one of the bases of life. Now, compounds are substances of two or more unlike atoms linked together. Water fits that mold. Water is a compound and a molecule. H2O has a hydrogen and oxygen. Those are unlike. These are represented by a formula. Here's another one. That is hydrochloric acid, HCl, a hydrogen and a chlorine, or sodium hydroxide, an Na and an OH fused together. And they look like that, ammonia, NH3. One nitrogen and three hydrogens formed together in a formula. Now, pure substance is going to have a definite composition. Homogeneous substance and pure substances are often pretty hard to distinguish, but a pure substance is just one thing: water, just water. Homogeneous deals with mixtures, a mixture that is coherent or the same. Pure substance is not a mixture. A mixture is just two things mixed together. By nature, it's not pure. When you're mixing, you no longer have really purity in the substance. And so mixtures, two or more pure substances mixed together but not chemically combined. Think about Kool-Aid or coffee. Kool-Aid is a good example. You take some Kool-Aid and then you mix it with some water, and what do you get? You get water and Kool-Aid. They don't mix. Or I should say, they mix, but they don't chemically combine. It's not like the water and the Kool-Aid make something completely different. You can actually separate the Kool-Aid out again if you'd like, by boiling the water. You'd be left with the Kool-Aid. They only mix. They don't chemically combine. Coffee is another example. You're making some coffee, and it's essentially made of the infusions of the coffee bean with water. Okay, it's not anything special. It's no chemical bond. Coffee is also a great example of homogeneous and heterogeneous mixtures. Homogeneous means it is a perfect blend where it's all evenly distributed. Heterogeneous means that it's not distributed well. Kind of like when I was a kid, I'd make chocolate milk, and I'd add too much chocolate in, right? And then you'd stir it, and all the chocolate would end up at the bottom. Delicious, right? Anyone eat it like I did? Well, anyways, the point being is that it's heterogeneous. It's not mixed perfectly. And homogeneous is mixed perfectly, like a good cup of coffee. Now, science changed a lot in the 1800s. A lot of men who had access to being a full-time scientist, and they discovered a whole lot of things. Really, science before the 1800s was done by priests and doctors and amateurs and their primitive laboratories, and all of a sudden you have guys who are paid to be scientists. They just all they do all day is just discover things. Turns out when you're paid to be a scientist and you're smart, you can get a lot done, and Dalton did that. He devised what's called the atomic theory, and he said that atoms make up the universe. Every element consists of tiny, indestructible particles called atoms, and he says that all the atoms of a particular element have the same size, mass, chemical behavior, and this is ingenious. This guy really came up with something that changed science forever. Before, what we see was the only things that exist. Or maybe they followed some Aristotle theory that everything was made up of some wombo combo of earth and fire and sky and water, and that didn't make sense. Now you have these little tiny atoms that nobody can see that make up everything. And John Dalton was mostly correct. It turns out we can divide and destroy atoms, we call that nuclear warfare. We are able to destroy those kind of things, and that there is some small variation in size and mass based on really the number of neutrons in a particle. But for the most part, he was right. And he said different substances act differently because of different atoms. Water and peroxide act very different. Just because the peroxide, or the hydrogen peroxide you might call it, has an extra oxygen in there. They're both made of hydrogen and oxygen, but in different quantities, creating severely different substances. We can see that with sugar. Sugar is made of carbon and hydrogen and oxygen. So is formaldehyde, what we store dead stuff in. And so different variations create wildly different products. And when you rearrange, combine, or separate atoms, you can create different properties. For instance, hydrochloric acid, HCl, can be formed by mixing hydrogen gas, a very flammable gas, which was used in many chemical processes, with chlorine, something that is just pretty generally useful as a substance with a high pH. Not everything Dalton said was correct. I said that atoms are not indestructible. World War II demonstrated that. Nuclear chemistry studies the propensity of atoms to change over time. Turns out not all atoms are stable. You look at your periodic table, you might see some of these elements. For instance, number 118 is called ununoctinum, and ununoctinum has some really strange properties. It doesn't even last a second. It is completely destroyed, goes through nuclear decay, and ends up being some form of like uranium in the end. And uranium is pretty far away from it on the table. Uranium is number 92. I mean, that's quite the change, right? Nuclear chemistry studies that. You also have two laws. Law of indefinite composition means the ratios of masses are the same. So water will always be about 88% oxygen by mass, and hydrogen about 11%. You can see that oxygen weighs 16.00 atomic mass units. That's under oxygen, number 8. You don't know what an atomic mass unit is yet, but you can think of it like weight. Oxygen weighs about 16 of any one given unit. And hydrogen weighs about 1.008. Hydrogen's a lot lighter. So what weighs more, 2 hydrogens or 1 oxygen? Well, the 1 oxygen weighs significantly more, 16 to 2. It comes up with a ratio. The law of definite composition. You also have the law of multiple proportions, stating that you can't have a compound made of half an atom. And that's true. You can't have an H2O 1.5. You split an atom and you cause some pretty severe consequences. Nuclear chemistry is that field that studies those things. And with that, we are actually done. You have Section Review 2.1, page 23, numbers 1 through 8 for homework. And you can't get started on that quite yet because we actually have one more thing to do, and that is our lab for today. While I'm away, we are going to be doing 2 labs, and these are not anything that you're missing out a lot on. And I think that the Abeka teacher does a pretty cool job with what he is doing. Now, I'm not sure whether or not you can hear him, but we'll see. And I'm going to kind of narrate my way through it so that you can have just a good idea of what he does and what you'll be doing in the future in lab. So this is Mr. Wrigley, and he is the science teacher at Abeka Academy. He's the guy we are going to be watching today. I don't think you can see me and watch the video, but he is currently demonstrating the correct procedure on page 15 of your lab book, if you can get that out. Page 15, it is laboratory technique 2. And he's going to be demonstrating the correct procedure of how to insert a glass tubing into a rubber stopper. So you see he takes oil there, and he lubricates the opening to the stopper, both openings, and he is able to take the glass tubing and push it through the stopper. This is useful. Sometimes you want the stopper to go into a particular glassware, and you use the glass tubing to go through it. And he shows a good example of that. Nothing really dramatic there. And that's part of lab procedure 1. If you would turn with me to page number 16, it also demonstrates how to use a balance. And most of the time in lab we're going to be using electronic balance, because the electronic balance gives a better reading and it gives a faster reading. Manual balances have to, it's a very, very delicate procedure in order to read them. And I'm not sure whether or not he actually uses one. Oh, he does. And let's see if he can explain himself here.
A triple beam balance, and we showed this to you in our initial lab for this series, the triple beam balance. Let's take a look at it here, and we're going to show you how to use the triple beam balance. You'll notice that I have here essentially 3 main beams that have weights basically on them, and by moving them down the sliders here, down these railings, we can essentially take the mass of whatever we're weighing. Now notice I said they're weighing. Now do remember, students watching, there is a difference between mass and weight. Mass is the quantity of matter. Weight is the gravitational influence on that mass. However, in chemistry, we have a tendency, even though when we're taking a mass, we still call it weighing, just for the simple fact that the term massing just doesn't sound appropriate there. So even though we are quote-unquote weighing the material, we are in fact taking the mass of that object. What we're going to take the mass of is for this rubber stopper. Now at this point, students watching, you don't need to record anything, but I'm just going to show you exactly how to find the mass of this particular rubber stopper. First of all, notice here that with this, the indicator here is for the most part at 0. Let me just reset the scale and see if we can get it more accurately there to balance at 0. Alright, that's pretty close. And so what we're going to do now, I'm just going to place the rubber stopper, and you'll notice instantly the scale kicks up. Now, in order to adjust this, I'm going to adjust with these sliders here, starting with the first slider. I'm going to move this all the way to 100, and you'll notice instantly now I'm too heavy because the indicator has gone now below the line over here. So I'm going to move the 100 back, and you notice it's now above. I'm going to move this to the 10. It's still above. 20, still above. 30, still above. 40, okay, now it's fallen below. So I know I'm too heavy, so I'm going to go back. There, I'm at the 30. Now I'm going to move the 10s, or the 1s, excuse me. 31, not enough. 32, not enough. 33, looks like too much, so I'm going to back off. Alright, so now I know I'm between 32 and 33 grams. Let's just go in a little closer here. You'll notice the last slider. This last slider represents tenths of a gram. So we have 0, 1/10, 2/10, 3/10, and so forth. And then each marking in between represents the hundredths position. So we're just going to move the slider until we get a balanced measure. And let's take a look at the needle over here and see if we're balanced. Looks like we might be a little under, so we'll just stay there until we get it balanced. And it looks like that does it. So let's go ahead and go back to the riders. And we'll notice here, okay, this is 0, so we don't count that. 30 plus 2, so that's 32, plus 0.26. You'll notice there, here's 0.25, 0.26. So this rubber stopper has a mass of 32.26 grams. Now, that was using the triple beam balance. What we're going to do to actually record the mass of this rubber stopper.
So anyways, you can write in your lab report that your stopper was 32.26 grams. And that is written under Part 2 using a balance on lab report sheet 3 on page 19. You can write stopper as the object, and the mass was 32.26 grams, and that is recordable. Under Part 1, inserting glass tubing into a stopper, all you have to do is write what was done, and that was to lubricate the tubing and the holes of the stopper with a drop of oil or glycerin. And you can write that underneath Part 1. Lubricate the tubing and the hole of the stopper with a drop of oil to allow it to move a little bit freely. Okay? And let's see here. Does he receive a mass of any other object? He does. So under number 2, he actually has a watch glass here, and the watch glass, he records a mass of 33.1, and you can see here that he went a little lazy and he got out his automatic recording device for mass, and was able to get that recording. The watch glass was 33.1 grams. Now, he also decides to use a graduated cylinder, and he shows you how to read a graduated cylinder. Now, when you read a graduated cylinder, you want to put it flat on the ground or on the table. You want to wait for it to level out. Then you want to read the bottom of this part, the meniscus. And you can see right there that it's approximately 21 milliliters in volume. And all he does is take a couple of tests just with water. So under trial 1, you can actually write 21 milliliters. And he does a second trial where he comes up with something a little bit different, and he records that as Mr. Wrigley. Let me see. That would be approximately 48 milliliters. And you can say that actually pretty exactly. You can see the bottom of the meniscus there of 48 milliliters. Almost exactly. You can put 48.0 if you'd like, and you would be correct using significant figures. Not that I say that for the rest of the year. That scares students away. Okay. Now, here is his next experiment. And this experiment, he uses a substance in part 4. The substance is called copper 2 sulfate, and it is a substance made of sulfate, which is sulfur and oxygen, and copper. And so this substance isn't super harmful. But he also uses another substance called sodium hydroxide, or NaOH, which has a sodium and an oxygen and a hydrogen. And that substance is very harmful. You can see on page 17 it says, under no circumstances should you allow sodium hydroxide to come into contact with your skin, eyes, or any mucous membrane. And what he does is he creates a filter, and this filter is able to demonstrate what happens when you combine copper 2 sulfate with sodium hydroxide. Let's take a look at what he does. Sorry, my screen froze there for a second. One of the things he does first, and you can see that this is 3.5 grams, is he puts copper sulfate onto, or actually inside of a dish, and he weighs this dish and weighs the copper 2 sulfate. And the mass of the copper 2 sulfate and the dish, and you can write this on your lab report, page 19, the mass of the copper sulfate and the dish is 3.5 grams. The mass of the dish alone is 2.2 grams. So the mass of the copper sulfate alone is only 1.3 grams. And you can write that underneath the subtraction line. There is 1.3 grams. Let's take a look as he mixes copper sulfate with sodium hydroxide inside a filter. He actually mixes it with water at a certain specified amount to get this copper sulfate to become a liquid. And he talks a whole lot. He demonstrates how to set up a filter paper. Let's watch that because that's pretty important.
Paper in order to filter the chemical reaction that we're going to have here in just a moment. So I'm going to take a piece of filter paper, and you remember, students watching, in the first lab we had a filter. I've chosen to use a plastic filter funnel here instead of a glass, just because they're a little tendency to be a little quicker. And I'm going to take this piece of filter paper and make a filter out of it. The way I do that is I first of all fold the filter paper in half, and then I go to fold it in half again, but instead of folding it completely in half, I'm going to do it slightly off to the side to kind of make this conical shape. And then what I'm going to do is I'm going to tear off this corner, and by tearing off this corner, this allows the filter to lay more secure in the filter funnel. So now what I'm going to do, if I open this up, you'll see I have a nice filter cone there. And this filter cone can go right down into this filter. And now, to have it adhere to the sides of the filter, I'm just going to simply douse it with a little bit of water to help it to adhere to the sides of the filter funnel. So as you can see there, we have our filter adhering nicely to the sides. Now I'm going to pull our ring stand around here, and I'm going to rest the filter right here in our ring stand. What we're now asked to do here at the bottom of your lab report page, or your lab page here, it says pour the sodium hydroxide solution into the copper 2 sulfate solution while stirring with a stirring rod. These substances will react as follows. We'll show you that chemical equation. Let's go ahead and react these substances, however. And we're going to pour down our stirring rod so that we have a controlled reaction. We don't want it all reacting at once. And you may notice here we have a blue cloudy substance forming. Let's take a little closer look here at the substance. Notice we were once clear. Now we have this blue cloudy mixture that has essentially precipitated out of this particular solution. Let's take a look at the board for just a moment at exactly what has occurred as far as a chemical equation is concerned. What we've done, we took copper 2 sulfate pentahydrate to be more exact. That means it has 5 water molecules for every 1 copper sulfate. But essentially, copper sulfate pentahydrate, and we reacted it with 2 moles or 2 molecules, if you will, of sodium hydroxide aqueous solution. What then happens is this, is sometimes what's referred to as a double displacement or a double replacement reaction, where the hydroxide will come off of the sodium and it's going to bond with the copper. And the sulfate will come off the copper and bond with the sodium. So notice what we have here. We have copper hydroxide solid plus sodium sulfate aqueous. And so you'll notice here that the solid material that we saw precipitate out of that chemical reaction is actually calcium or copper hydroxide in that particular instance. So this blue cloudy substance is copper hydroxide. Well, what we're going to do now is we're going to filter this particular substance. So we'll go ahead and put our empty beaker under here. Again, using our stirring rod as a control for our flow, we're going to filter this substance out, making sure not to go above the filter line. And you'll notice that we have some of the liquid material dripping out the bottom. The substance that is dripping or passing through the filter paper is referred to as the filtrate. So this substance here is the filtrate. What will be left in the filter paper when we're done here is going to be the residue, or also referred to as the precipitate in that particular instance. So students watching, what we're going to do is we're going to let this filter out, and we'll be back in just a few moments to show you the results of this filtering. Students watching, we've waited several moments here, and we've filtered our substance. And you'll notice here we have one last drop coming, so we'll go ahead and collect that. Notice that our filtrate here is still a little blue. That's because some of the precipitate did manage to get through the filter. We could get that out by simply sending this through the filter again. But I want to show you inside the filter, and you'll notice here this blue precipitate, this blue residue. That is a solid material. That is copper hydroxide solid there. And so that is the blue residue, or the precipitate that is left over from our filtering process.
Well, there you have it. You have the first chemical reaction, unfortunately, virtually in this class. The mixture of copper sulfate and sodium hydroxide to create copper hydroxide and sodium sulfate. And you have a precipitate, which is a solid left behind that was once a part of a liquid material. Now, to flip to the back, page 20, and I'm going to hurry here because I understand class is probably ending. To what decimal places can the masses be determined? It goes to, our balance goes to the tenths place. The tenths place. What did you observe when 2 solutions in part 4 were mixed? And that is, you observed a blue precipitate. And number 3, you're going to have to sketch on your own. I wish you all the best, and hopefully I will see you on Wednesday. Goodbye.